numerical method 2 class. So last time we were talking about degree of precision of a numerical method, particularly of quadrature rule, which is a numerical method to approximate a definite integral. So we saw that the easiest way to prove that the degree of precision of a numerical, of a quadrature rule is n, is just to show that the error term at x to the k, where k runs from 0 up to n being the degree of precision of the quadrature formula. So we show that the error of that monomial, of those monomials, is 0, and the error of the monomial to the degree of precision plus 1, that is n plus 1, is non-zero. And this is much more simpler to prove than to substitute a full polynomial of this form. So that's the main advantage to do that. So what we did last time, we took the trapezoidal rule, which is given by this right-hand side, h by 2 into f0 plus f1. So what we did for this formula, we use this one, obviously. We use the error term because here we use the fact that we know the error term. But what if you don't know the error term? Just imagine you only know this formula, but you don't know the error term. You don't know this part. So that's the second thing that we are supposed to cover today. Because I said that assume that this is not known, the error term. Just assume that. And in most of the cases, you will not be memorizing all these error terms. The thing that you really need to know is the formula. Right. Now, if you have the formula, because this is what you really need to know, particularly for the 3, and the last one, the Boole's rule, is rarely used. So if I encourage you to remember, is this 3, yeah? Or at least these 2, trapezoidal rule and Simpson's rule, at least. But at most, you can go up to the Simpson 3/8 rule. That would be good. All right, so now let us do that. Let us do this. That's what we are going to tackle today. Kashopi, welcome. Okay, so oh, Janice, you're also there. I greet you. Good. So this is where we stopped last time. We assume that the error term is none, and this is the expression we use that we substituted, and we prove that this condition with xn is satisfied. Yeah. Okay. Now what we are going to do, we assume that we only know the quadrature formula. We don't know the error term. So we can write the error term as the difference between the integral and the quadrature formula from, I think I wrote it before. Anyways, this one. So we are going to use this formula. So I assume that it's not known explicitly. So if it's not known explicitly, we can always write. We can always write as minus so this is what we'll be able to do. I can always integrate, right? Any function anyway. When the function is simple to integrate, I can always perform this. And the quadratic formula is there. It's just expression of the function. So the only thing I need to know is the function I substituted. So we are going to prove the same thing. So for the trapezoidal rule, we are going to prove this. We are going to prove this one. So we are still here for the trapezoidal rule. So we can write that E x to the k is equal to what? The integral, which we can always perform obviously this is a dummy variable. I can leave x or t. So you can put t, d, whatsoever. Then in that case, I'll put d x minus the quadrature formula for x to the k. Okay, so this is what we have. So now if you use the quadrature formula here, already this one I know, a and b are x0, x1, right? So that this is equal to, I can substitute the integral. So the antiderivative of this, okay, we say k would take the values 0, 1, only two values. 0, 1, yeah. And 2 will be the last one to show that it's non-zero. Okay, now, k cannot be -1, right? So I can use this. So this will be x0 to x1, which is a, and this one is b, right? Good. Minus h by 2, this is the formula. And then I take this function at x0. So if I substitute this at x0, that will be x0 to the k. Yeah? Plus x1 to the k. So this is what e k gives us. Now, if you take k equal to 0, now we need to prove k equal to 0, k equal to 1. So for k equal to 0, e x0, which is e1, will be equal to what? If I substitute x here, x is what am I even saying? Oh yeah, k is equal to 0. Okay, now if k is equal to 0, we substitute here. This is just x, right? So this will be x This is 1. Any number to the 0 is 1, 1. So this will be 2. Now you see that 2 will cancel out with this one. So let me write it. So this is h by 2, 1 plus 1. So that's what this gives us. Now, what is this? X at x1 is x1 minus x at x0. So this will be x1 minus x0. So this is x1 minus x0 minus h by 2 times 2. So you see that these two cancel out. So this is equal. Okay, you see that this is the difference between two consecutive terms. x1 minus x0 is h. So this is h minus h, which is 0. Now, if k is equal to 1, k is equal to 1, I substitute 1 here. You can see it's s squared by 2. So e x will be x squared by 2 from x0 to x1 minus h by 2. Now, this will be x0 plus x1. Okay, now, and what is this equal to? So you can see that this, if I substitute, this will be x0 plus x1, or x1 plus x0, h by 2. This one, if I evaluate this, it gives me that, right? Because this 2 is there, remember that this is x squared, so this will be x1 squared minus x0 squared, which I can factor. So if I factor, I will get this times that. This is the difference, right? x1 minus x0 is h, and then x1 plus x0 is this one by 2. So that's what I wrote here directly. So minus, oh, it's already even in that form. Minus, so I can take this to the right hand side. I mean, not right hand side, but to the this factor I can permute, right? So I can permutate this one. You can change the position. This is like AB is equal to BA. That's why if I rewrite this, so that would be minus x0 plus x1 h by 2. So same number subtracted, subtract 0. So that one also gives you 0. Now you have to show that when k is equal to 2, then this error is not 0. So now if when k is equal to 2, so similarly, x3 by 3. So this will be x3 by 3, x0, x1. And then you come here, h by 2, right? x0 square plus x1 square. Now you can substitute this expanding factor. You will show that this is different from 0. Now I'm asking you to show it. That is different from 0. Do the calculation yourself. Expand this and factor, because when you will expand, you will get this. Obviously, you have that factor here. You see, and you can write this as x1 minus x2, like this. Factor of, right? Of this difference, and this already gives you h. This is h. And you have the other term here, right? And what would be this term? Here you have x1 square, right? Plus or minus x1, x0, x1, something like this. Then plus x0 square, or I can start, yeah, x0 square. Right, something like this. Obviously, if you expand this times that, will give you this term. This times that, the last one, will give you this term, right? And then you have the inner product there, because we already multiplied the first one by this one. You still need to multiply this and that. So the remaining terms, so I have these two terms. The remaining terms will be the negative x0, x1 square when I multiply this by that. And then by this one, will give plus x0 square, x1. And then if I take this one and multiply by the first, this one, it gives minus x0, x1 square. And finally, this and this one will give plus x0 square, x1. You can see that x0 square, x1, x0 square, x1 will cancel out with this one. And this one will cancel out with this. No. So this one is not canceling here. Wait. What did I even say? Okay, so I say this one, this one times that gives us this one cube, and negative this one, and that gives this cube. Okay, now I have these two and that two. So I have x1, that's negative x0, x1 square, yes, and then plus x0 square, x1, yes. Now minus x0, x1 square, yes, plus, all right. Now, what are the terms that are canceling? Okay, so this one, it doesn't, it's 2 times, so I have to change the sign. So this is plus. Now, if I put plus here, I think things will work. Yeah, so okay, this will be plus, not minus. So if I put plus here, so the first one, this one will be plus, right? This and that, and the other one will also be plus. Good. And now finally, this one times that will be minus, yes, and this that will be also minus. Good. So you can see that this one will cancel out with this, and this one will cancel out with that. Good. So it's plus here. So you can see that we already have this term, which is h. Okay, so as I was saying, so you just substitute the, okay, so we are here, you substitute that, it will give you this one. So this part only will give you this. So we 1, so this is 1 by 3 h. And then you have these remaining terms. So you have x1 square, you can see x0 square, x1 square, which is similar to this one, appears here. So we can write x0 square plus x1 square is this one, x0, x1, plus this factor, plus x0, x1, right? So that's for this one. Now minus h by 2 x0 square plus x1 square. So you can see that this term 1, 2, 1, 2 is similar to this 2 term. So you can see that you can show that this will never be 0. So that's what I want you to show. Right. So if you want, you can group, you can split this, you can split this, you can split this if you want, and put this term and this term together, isolate this one differently, and show that it will never give you 0. So that's what I want you to show. So you should show that this will never be 0. Okay, so this is like the expansion that you'll be performing. Now, you use this expression, group the term, and show that it will never be 0. Right. It will never be 0. X1 and x2 are two distinct terms. So x1 and x2 cannot be equal, right? They cannot be equal, this one. Because you are moving from one point to the next point, so they are different. So x0 is different from x1. They are not equal. Because if they are equal, this integral will be 0, right? So they are different. Because you can see that h is the different. So h is not 0, right? So you use that, right? To show that this is always 0. Non-zero. Always non-zero. Okay, so that is it for this one. Now, what is the next step? Okay, so we are done. If you want to show, as I said, the degree of precision of a quadrature formula, if you know the error term, it's easy. But if you don't know the error term, you proceed this way. You write integral minus the rule, and then you substitute the x case when k runs from 0, 1, 2, up to n. You show that e x to the k will be 0, and then e x to the k x to the n plus 1 is non-zero. Okay. So I hope things are clear now. Okay, now we'll move to the next. We'll proceed with the next section. Is there any question? Okay, I will give room for questions. Is there any question? Simeon, welcome. I don't know when you appear, but you are late. Oh, you join us late. Is there any question, Simeon? Any question? Simeon, any question? You cannot hide, eh? You cannot hide. Any question, Kashopi? Johannes? Nanuna?
No question, sir.
So far, so good.
Yeah, I don't have any question at the moment. Yes.
So the concept, everything is clear.
Mm-hmm. For now, yes.
Okay.
No question, sir.
Okay, now let us proceed with the next. Let's move to the next section. Okay. Okay, now this theorem is just to prove these results, those ones, the degree of precision of the various methods, right? Because this is you have a theorem. This is a theorem, and you have a corollary. The corollary for the theorem is this one, because here it gives us the rule. But because it's an approximation, we know that there's an error term. So this corollary gives us the error term, right? And now here for the proof, we need this theorem, the weighted mean value theorem for integrals. The theorem that you know is the mean value theorem. You know this theorem. But now we have a version for integrals, which is called weighted mean value theorem for integrals. So that is a theorem that we use to prove this formula. These ones. And for that, because this is a Newton code formula, don't forget. And we said that Newton code, what is it? In the Newton code quadrature formula, what we do, we replace f with this what? Interpolating polynomial, and we integrate. So that's what we perform here. You see that this is the function f, this is interpolating polynomial, and this is the error term, right? This is the error term in the interpolating polynomial, and we integrate this expression. Already Pn, if you use the Lagrange interpolating polynomial, this is how you write your Pn. Now, if you integrate this function f of x, this is what you get. And you can see already that from Pn x, you have this expression that you integrate. And since f of xk does not depend on x, you can take this out of the integral sign. So what will be integrated will be the cardinal function lkx dx. And that's what gives us the omega k, or the wk, this one. And you can see where wk is this one. Just write this properly, it will give you this, where wk is this, the integral of the lk's. Now, integration of the error term, that's where you need to manipulate the integrand properly using this theorem. Because in this theorem, you have to take one of the factors out of the integral using the mean value, or the weighted mean value term. And these are the conditions of the theorem, which we apply here, right? So if you apply that, it gives us the result, or the expected result. You can see that the error term will be given by this, which, if we define the wx to be this factor, we can apply the theorem and take this factor out of the integral, right? This will play the role of our f. You can see we take this one out of the integral. And we can only do it through this theorem. You can see that this first function, which satisfies this condition, and the second one is an integrable function on the closed interval AB, and it doesn't change its sign within the interval AB. So that will be our G. But f is the function that is continuous. So if we use that, we can apply that to f being a continuous function, because from Taylor expansion, yeah, we can call it Taylor or whatsoever. The function f is supposed to be what? Continuously differentiable, meaning that the derivatives are continuous. So since this is a derivative, it's like the function f which is continuous over that interval. And g has to be integrable, because when you take f out of the integral sign, if you write integral of something, that thing has to be integrable, right? And that is the case for this function, which we call wx. This is an integrable function. It's a polynomial. So a polynomial is an integrable function, and it doesn't change its sign within. Right? So if you apply that weighted mean value theorem for integral, you obtain this result. Right. So please go through the proof. It's really easy. I encourage you to read and see how the error term for the trapezoidal rule is obtained. You can really see everything is detailed. I encourage you to read it. And we'll stop here for today. And we will continue next week, Monday. So happy maths weekend. Happy maths, right? Happy math means over the weekend, don't forget to eat your mahangu. Yes, nobody can even remind you about it. And you will swallow. You can even swallow a whole pot for yourself. But remember, you have to do maths over the weekend. Happy maths. Okay. Thank you for your kind attention. I hope you enjoyed the class. If you didn't enjoy it, anyway, me, I've enjoyed it. It was so sweet. And I hope you will enjoy even later on. Okay, enjoy your weekend. Happy maths. Bye-bye.